So this is the beginning of the second set of the slides of chapter 2 on instructions. And we're going to keep on covering the groups of instructions that are available in the Legate, the subset of the ARM ISA that we are studying. And now I want to present some bit manipulation instructions that are pretty much available in every ISA, and how they map to some operators in C and Java. So we have shift left, shift right, the and immediate. So these are bitwise operations. Bitwise OR and OR immediate, and bitwise the not instructions. So you already know how for example, the difference between and immediate. So and would be operating on two registers and putting the result on another register, but and immediate would be operating on the contents of a register and an immediate field that is embedded in the instruction itself, and then putting the results in a register. And what we mean by bitwise or bit by bit operations is that each bit at its position is, in the case of the AND, is ANDed. So if the least significant bit is 1 of one operator, and the least significant bit of the second operator is 1, then the AND would be 1. The least significant bit of the result would be 1. And the same thing happens for each of the bits, for the OR. And then for the NOT, we are not comparing two operands. It's just a single operand. It's just that each bit is being inverted. Okay, so that maps well to some operators that are available in high-level languages. And then the shifts is just shifting the bits. So if we are shifting the bits left, then the least significant bit goes to the left, so we come to the next more significant bit, and then a 0 is inserted into that least significant bit position. If we are shifting right, then the most significant bit becomes the less significant bit to the right, and then a 0 is inserted as the most significant bit. So those are called logical shifts because they are not taking into account the sign bit and things of that nature. So we may talk about arithmetic shifts, but this group of instructions are considered logical type of instructions. That's when you have in the data path, you have the arithmetic logic unit, is because that unit is doing all the arithmetic, so doing addition, subtraction, but it's also doing these operations as well. So I was talking about the shift operation and how it uses the register type of instruction and that format to specify how many bits to shift in the shift amount field. And you can see that it has 6 bits. So it allows us to specify from 0 to 65. And since our data word size is 64 bits, it allows us to specify from 0 to 63. And since our data path width is 64 bits, then we can shift any amount of bits that we want. So this is very useful. Shifting left. If you only are working with unsigned numbers, so you can get very efficient division and multiplication by powers of 2 by shifting left or right, and is done on a single cycle. So there is a very efficient type of hardware, which is called a barrel shifter, that can be implemented to do this type of manipulation of the data in hardware. So here are some examples. If we were going to AND the contents of registers 10 and 11, and I guess put it on in register 9, you can see here that these bits are 1, but the corresponding bits are 0. This is 1, this one is 0, and this pair of 1s has a corresponding of 1s over here. So if we were to do the bitwise ending of that, then we would basically have these 2 bits survive. So this type of bitwise operations are useful for manipulating subfields of data. So in this case, if I was just interested in knowing if these 2 bits are 1 or not, I could mask everything else. Okay? And I could mask everything else and I could get that information. The OR operates the same way, bit by bit OR of the data. So in this case, you can see that these 2 are 1 and these 2 are 0, so we get 1, the ORing of that, and so forth. Okay? This allows us to leave some bits unchanged and just change the ones that we want. If we want to, actually allows us to set some bits to 1 and leave the other ones unchanged, and that's part of masking operations in binary numbers and binary patterns. And here's the NOT operation. Where we would essentially invert every bit in register 10. Now let's talk. Now let's start talking about conditional operation. So essentially, operations that we use to change the flow of the program, and we can do that conditionally or unconditionally as well. And if you think about having operations to do arithmetic and logic, and then having operations to do branching or altering the flow of the program, this is pretty much all you need to start converting a high-level language type blocks or constructs like loops and ifs type of statements to schemas and models that allow you to build a compiler. So at a first order, a compiler, after it does the parsing of the lexicon of the language, of the syntax, what it's going to do is to identify these well-known blocks. And the compiler has schemas and models built and blocks built in assembly to handle if else type of structures, different loops, case statements. So all that combined with the data manipulation and the instructions for altering the flow of a program allow you to transfer or convert that high-level language to assembly. And once you have assembly, essentially it's a lookup table operation to translate it to the actual binary patterns that are the instruction of the machine. Now, mixed in there is the optimization part of what a compiler does, which is making sure that the accesses to memories are minimized, and that you use as much register as possible, that the data lives in the register file for as long as possible, and things like that. But at a first level, to do just the conversion of a high-level language to machine language and be able to run that program on an actual processor, you're just looking at translating that via this well-known type of blocks that involve data assignments and flow control that alter the flow of the program. So let's look at some instructions that aid in doing that in the ARM Legate ISA. So the conditional branches, it branches to what we call a label. Now in assembly, a label is really a memory location in program memory space. And that's another thing that the compiler does. Another big part of what the compiler does is doing association of the mnemonics that get transferred from a high-level language into actual binary addresses and as well as registers in the register file. So the label here really represents an address. So this is a symbolic address that is going to get resolved later on it could be resolved by a linker if you're doing a static linking, or it could be resolved later at runtime if you are doing dynamic loading or if you're doing dynamic linking. But the point is that this represents an address. So in this case, we have the conditional branch on 0. So it tests the value of a register, and it changes the next instruction that gets executed after this one. If the contents of the register is 0, the next instruction that gets executed is at this address in program memory. Then we have the conditional branch on non-zero. So that one, it tests the source register. And if the value is not 0, then the next instruction that gets executed is the one that resides at this address in program memory. If the conditions are false, then it does not branch. Then the instruction that follows the branch instruction, or what is called the fall-through path, is taken, and that's the instruction that gets executed. Then we also have an unconditional branch. So essentially a branch. In many ISAs, branches are referred to conditional type of flow control, and then the unconditional ones are called jumps. But that's just sort of a preference of different ISAs. In the ARM that we are looking at is also called an unconditional branch. So it just goes. If it hits this instruction, it's going to jump or branch unconditionally to the instruction that resides at this address in program memory. So let's start looking at how a compiler would try to use these instructions to convert certain blocks and constructs of a high-level language like C. So this is an if-else type of a structure. So if I equals j, we have this assignment here, f is equal to g plus h. Else, so this would be the fall through, f is equal to g minus h. So this would be the fall through in C. Now let's assume that the variables f, g, h, I, and j are associated by the compiler, so all the data movement that needed to happen to bring them from memory already took place. Let's say that those 5 variables are in registers 19 through 23. So we could start by subtracting register 23 from 22 and assigning that to register 9. So essentially, we're trying to create that zero condition, because if we subtract two numbers and the result is 0, then I know that they are the same. So essentially, we are subtracting j from I. If the result is 0, I know that I and j are the same. So the compiler knows this, that it can use that instruction to force the condition. Then we test for non-zero, and we branch to else, the else part, which could be several lines. In our case here, it's only one line, but it could be several lines of assignments. So if x9 is not 0, we know that I and j are not the same, so I have to take the else path. So that's why we have that branching there. If I don't make this branch, then it means that I and j are the same, because I can only have two outcomes. Either this result is 0 or is not. If it's not 0, that means it is 0, and that means that I and j are the same, so I'm going to take the primary path here and add g and h and assign it to f. And then I have an unconditional branch to the exit of that structure block that is implementing the if-else. This is the else part. So you're going to see in assembly that the labels, they are placed on the far left of the instruction lines. So if this is true, if x9 is not 0, then the next instruction that gets executed is this one, which is a subtraction of h from g, placing the result in register 9.
Professor, it's 145.
Okay, thank you.
You're welcome.
And this is the exit. This is a mistake over here. This should be 19, because F is in register 19, and that's what gets a subtraction of H from G. So this line actually is incorrect. So this should be F over here. That should be 19. This one should be H, so that should be 21. And this should be G, that should be 20. Okay? So in essence, this this should be the same as this 19, 20, and 21. This one's okay. All right, so I'm going to stop here, and I'm going to see if there are any questions about what was covered.